so it is to that level. Now let's now go into the fluent simulation, how to set that up. So before that, let me close off the ICEM window, and the project is already saved, so no. So this Fluent that I'm using is the 2023 version. What is the version you guys have here? 19. And I have used 19 fairly recently as well, so whatever files that I have should be fine on ANSYS, on 19 as well. Okay, so as you launch Fluent, this is a 3D simulation. Find double precision. Depending on how many processors you can use on your machine. Let me use 12, but it's of course a function of the system you are using. So on a typical laptop, personal laptop, 4 processors should be fine, stable enough. So start. I think the Fluent layout changed drastically from the 15 version was very different, and then it changed drastically, and then otherwise it has been very similar since then. Okay, so now the software is launched. The first thing that we have to do is bring in the mesh file. So let's go to file, read mesh, and let me go to the corresponding folder where I have this work. Go to lab data. So I'm picking this UNC071 file. Okay, so now the mesh is in the Fluent platform. The first thing that we'll do is check the mesh quality again, because still at this stage you can find some errors and then the simulation won't work. So check mesh, and I think it is done. It did some improvement on the path line tracking, particle tracking. That is not relevant at this point. It's the flow simulation that we are going to develop next. Go to scale under the general, because this is funny. Once everyone in the has Chandan visited here, Chandan Bush. Did you guys attend his talk, Chandan? Online lecture. Did you attend his talk? Chandan Bush. Yes, so Chandan is our junior from JUDES. So Chandan does open form modeling. So we decided that we should collaborate, and I shared one of my geometries with Chandan, and he was supposed to develop the open form simulation and was supposed to compare the data with the fluent work. Now, of course, he was done with the simulation, and then we started to track the data, and it's as we found out, the pressure drop needed to generate similar flow rate was very high in open form. Can you guys guess why that was the case? It shouldn't be the case, right? Because of the dimension. So when I said that the CAD software, the ICM, is dimensionless, it just does not tell you whether it is in millimeter format or meter format. We know from experience that the length is equivalent to a millimeter. But when you import that mesh, or you export and then you import that mesh in your computing platform, you don't know about the length scale. So Chandan did not change anything on that. And as a result, what he was modeling was what you have over here. So right now the Z direction is basically this direction from the front of the nose to the back, and the dimension comes out to be around 100 meters. So it's a huge person. Like I think Devrananda yesterday was telling me of Professor Shanku's story where the human being got tremendously big. So it is that big of a person. Have you guys read Shotajit's Ray? You haven't. So basically, if you think about the pyramid as the tip of a nose, it is probably as big as that person. So you need to be careful about the scale, the length scale, and that is something that if you are working with other comparing platforms, whatever that conversion length scale is, you need to be really careful about. Otherwise, even after months of hard labor, things don't go to anywhere. So over here, go to specify scaling factors, make it 0.001. We are trying to convert to the millimeter scale, and scale. So now see what shows up. So 0.114, 0.115 meters. How much is that? 11.5 centimeters, right? So if you think about the dimension of your own head, 10, 12, 13, 14, 15 centimeters is what you get. And make sure that what you see on the screen, you don't trust it blindly, but it is physically realistic because you are developing a biological model. So now that has been set up, and of course the scaling factor should be same on all x, y, z because you don't want to give an aspect ratio to anything. So once that is done, close, and then this is going to be a pressure based solver. So the flow is driven by the pressure gradient. Should it be steady or unsteady? Based on our understanding of the mathematics from the first few days, unsteady, right? So that is key towards what we did yesterday, that in the upper respiratory tract, the time varying component is strong, and that should dictate what you choose over here. If on the other hand you are trying to model transport in the bronchial generations, if you are past that conducting phase, you can use a steady state simulation. And typically, if you do read the medical journals where they do this kind of modeling work, they never really explain anything on this, and I can assure you that most of the times they would use steady state simulations for upper respiratory tract. But we are not doctors, we are the useless kind of doctors. So we need to make sure that we understand the physics and apply the simulation accordingly. So transient. And after this, you can turn the gravity on. I do turn the gravity on, but as I said yesterday, the gravity effect on the flow flux is minimal. It becomes prominent with the particles. But since my eventual goal here is on drug delivery or infection transmission, I'm going to turn it on. But if you are coming across a problem where you are not tracking the particle transport, it is just the flow simulation some kind of heat transfer effect. That is a very big area of research as well, where we have some papers too, where you think about the flow going through the complex pathway and how is that warming up the air. I think we were discussing about this couple of days back. The nasal passage is very tortuous, so when we are inhaling the very cold air from outside, the air gets warmed up before it reaches the lungs, and that is a heat transfer problem. There, you don't need to turn the gravity. But since here the eventual goal is to get the particle transport data, let's turn gravity on, and then you can assign what direction you want the gravity to be. So again, this setup is, as you probably recall from my slides from yesterday and from some of the lecture materials, if this is the nose, I have the Z direction from the front of the nose to the back, the Y is up, and the X is into the plane of the screen. So based on this, the Y should be negative 9 point the G value. Now, there are again some clinical studies where they have found that if the person has some kind of sinus inflammation, we want to send drugs to the maxillary sinus, which is that big sac on the two sides. So the doctors, they recommend the patients to lie down on the side and then apply the nasal spray. If that is the case, then think about what the corresponding direction of gravity should be. So this person is then lying down. So basically, it is oriented in the X direction, and you can control that from here if you are trying to model drug delivery when the person's head is inclined in a different direction. But here we are just trying to get the normal condition when the person is walking, sitting upright, and negative 9.81. So this is all for the general model. Let's now go into the fluid mechanics modeling. We are going to set it up as an LES model. So viscous SST K omega. I do remember the individual numbers, but just in case, I don't think I have the protocol here either, so that's fine. But you will find the relevant parameters that you have to set up on the LES simulation protocol. But over here, let's go to large area simulation. Now, what subgrid scale model would you use? Have you done LES, like the mathematics of LES modeling in any of the CFD courses? You have?
No, actually, I think Douglas module there is a course,
Yeah.
but it's launched before they have already finished the questions.
I see.
Most of the fields, so it's launched last year.
Okay.
Most likely they have.
So what LES model does in very brief, if I try to describe it very briefly, it develops the general flow profile, but it needs the support of a sub-model that would resolve the smaller fluctuations. So along with LES model, you have to choose a subgrid scale model to resolve those fluctuations. Now, it is up to us what to use. What we do is use the kinetic energy transport model. But then again, you can look up each of these models and try to figure out why you should be using which one. I do plan to use the well model next because what I found out from my attending different other sessions at the conferences, that the well model could be equally potent, if not stronger, for geometries that are very complex as we have over here. But for the timing, we are going to pick kinetic energy transport model, and that is what we use in our published works as well until now. So click OK. So this error comes up because of a certain reason which I'm going to show later on, but it is automatically changing the numerical method to something else. I'll come to that in a moment, but let's click OK for now. Okay, so the viscous laminar, let me just quickly double check one more thing. Yes, so LES and kinetic energy transport model. Okay. Now, Let's, so the discrete phase option over here, we have to set it up accordingly when we do the particle tracking. We are not doing the particle tracking yet, so we don't have to worry about it. Let me see if I can make it bigger. So the discrete phase is for particle track. Let's not change anything over there. Let's come directly to the materials. And under fluid, we are modeling air. Now these are the generic density and viscosity values for air, outside air. We are modeling air that has been inhaled in, which is typically warmed up. So based on literature, we would change the values. The density should be 1.204 and the viscosity should be slightly higher, 1.825. And then change, create, close. Now let's go down. Let's come to the boundary conditions. Double click on the boundary conditions. This is the inner material, the meshed space. We don't have to do anything in there. Left airway is a wall. We can keep it like that. For you can check what it means. So if you go to edit, it shows up as a stationary wall with a no slip boundary condition. If you want to apply some kind of wall effect, you can do that with UDFs at this point. I'm not going to change anything. Now later on when we do particle tracking, this DPM option is going to show up. And there you have to figure out whether the particles should be trapped at that wall or reflected or do something else at that wall. Since we have not set up the DPM here yet, that does not show up. So this is fine. Close. What we need to be careful about at this stage is what are your inlets and what are the outlets. And especially this gets a little confusing when you have the mouth included, the oral cavity as well in the model, but this one doesn't, so that is easy. So the left nostril is actually the plane on the left side of the nose. So that is going to be an outlet. So that is wrongly defined here at this point. So we are going to change it to pressure outlet because it's a pressure, sorry, it's an inlet. So that's where the air is going in through. So it's a pressure gradient driven simulation. So pressure inlet would be left nostril. And then as you change the kind of wall, this shows up. So you can assign the gauge total pressure, which is where if you are doing something else in terms of your pressure specification, you can assign other values as well. But as I showed during the lectures, it doesn't really matter. It is the delta P that matters. So I'm going to keep it as it is over here. So apply, close. The nasopharynx is wall, fine. The outlet is the outlet at the base of that tube after the nasopharynx. And I'm going to change it to pressure outlet because it is again a pressure gradient driven simulation. Having said so, from our experience, we have found out that if you have very thin channels, sometimes the outlet vent option might work. When you actually, instead of the volume flow rate, you actually specify what is the mass flow rate through the system. But for now, on this simulation, we are going to change it to pressure outlet. And now we have to figure out what should be your gauge pressure. It is going to be a value that is smaller than the one at the nostrils, right? Because high pressure to low pressure driven flow. I would suggest that use some trial value, say negative 50 pascals, but you use the targeting. So target mass flow rate, you specify that, and then figure out what should be your targeted mass flow rate. Now in this work, we are trying to model 30 liters per minute. So So 30 liters per minute. So we have to convert 30 liters per minute to what is the unit over here? It is in kg per second. So we have to convert that to kg per second. So the rho of air is 1.204 times 10 to the power of minus 5 kg per second, right? That's what we picked, right? For the density of air, let me just quickly check. So go to the materials, air, 1 kg per cubic meter. Sorry, this is density. Sorry, my bad. So this is the density of air. So you have to use this to figure out what would be the kg per second rate for 30 liters per minute. Let's go to where we were. So the conversion should be, if I'm not wrong, 30 times 1.204 divided by 60 times 1000. So 60 for the minute to second conversion, 1000 for the cubic meter to liter conversion, then 1.204 is the conversion from volume to mass. Can you give me this number? 0.6 into minus 3 kg per second. So 0.0006 kg per second. So we can set that thing up over here under the targeted mass flow. So 0.000, how many zeros? 3 zeros. So 6. So this is where you change when you are trying to simulate a different flow rate. Then you press apply over here. Okay, just to double check, let me see if it got activated. Yes. Is it 3 zeros or 4 zeros? 3. Okay, now 6 times 10 to the power of minus 4. Yeah. So right airway is still wall, right nostril is not wall, so we have to change that as well. So it is where air can go through as well. So pressure inlet, and as you change the wall type, this window pops up, and it is also at 0 gauge pressure. So apply and close. The tube is a wall. It is the tube at the base of the nasopharynx. So all good with the boundary conditions. You don't need to worry about anything until the reference values. So the reference values, I personally consider it to be a good practice to update the values over here to what you are using for the material property. So 1.204 and 1.825. Okay, so that's there. Now come to the methods. So under the methods, we are going to use Simplec, and let's keep everything second order. But one thing that I did a mistake on a few months back with one project was, for the transient formulation, you should use either second order implicit or the bounded second order. So I think I have updated the protocol accordingly. Don't use the first order implicit because there could be some errors. So let's use bounded second order implicit. And in fact, now with the with the more recent versions of ANSYS, they also given a warning like this here. The current turbulence model should only be used with bounded second order implicit. Okay, so let's go to the controls. This is all fine, but for example, if you have heat transfer going on in the system as well, then from this equations menu you can pick the thermal equations as well. Let's go to the monitors and the residuals. So now you have to figure out the residuals for the proper convergence, and then for that as well you need to look at literature to figure out what is the accepted standard. So for the continuity residual, we are going to use. Uh, could you guys open up the protocol? It should be oh, 10 to the. I don't think it's 10 to the power of minus 6. It's a mix of 10 to the power of minus 4 and 10 to the power of minus 5. I don't remember which one. So I don't think I printed this protocol, did I? No. So let me remember. So this is 10 to the power of minus 5, the continuity. If I'm not, 10 to the power of minus 4 is continuity, and the x velocity, y velocity, those are. Yes, so this is 10 to the power of minus 4, the velocity components, and the continuity component is 10 to the power of minus 5. You can pick 10 to the power of minus 6, that's fine. Even with picking so small values, you will see that sometimes the simulations don't reach, the residuals don't reach those orders. But if they stabilize, that's all that you can get in terms of convergence. So let's close it here. But when you run the simulation yourself, do take a look at the protocol for the correct values if I'm wrong here. So okay, and then 10 to the power of minus 4 for continuity. And what about the velocities? 10 to the power of minus 5. Okay, so 10 to the power of minus 4 for continuity and 10 to the power of minus 5 for the velocities. Okay, now let's come to the initialization, and there I would use the standard initialization and compute from, you can pick any of the inlets. There are two inlets over here, both the left side of the nasal airspace and the right side. You can pick either of the two. Let's pick right nostril and then initialize. I hope something is going on. So the earliest the fluent simulations that you guys have done, what kind of flow model did you use? Okay, SSD. What about you? And there are some studies where they compare all these different kind of turbulence frameworks, like which one is suitable for this kind of geometry. Typically, it doesn't take longer. As long as this, I think there is a lag in what we see on the screen, and something is going on. I trust that it worked at the back end. So let's see if we can now start the full simulation. So over here, let's think about the time steps that we are going to use, and there are a couple of papers on what you need as the proper time step size. There were a couple of publications back in the early 2000s, 2010, 11, where they looked at geometries as complex as this one, and they tried to figure out the best possible time step, in the sense that longer is the time step, quicker would be the simulation, right? If you're trying to track a certain interval. So for 30 liters per minute, the 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 consensus was the time step should be point triple zero two. Sorry, yeah, you're right. So the time step size is over here, right? Yeah, 0.00. Sorry. And now comes the number of time steps. So typically, you have to decide what is that interval of time needed for the flow to stabilize in the airway. You can pick any number of time steps. The simulation that we are going to use for the particle tracking, if you open it up, you will see that I have used 1750. So what is 1750? Think about 1750 multiplied by 0.0002. It is around 0.35 seconds. So that's the interval of time I used to consider that the flow to be stabilized in the airway. And based on the size of the airway and the flow speed, which is on the order of meters per second as we saw yesterday, that is sufficient enough. And of course, that number, the choice of those numbers are backed by other papers that have been out. For now, to show you how it feels like once you start running a simulation, let me just pick a very short, small number of time steps. Let's just pick 50. But of course, you are going to pick something much bigger. And then go to, I think the rest, the iteration, you can change the iterations as well. If you make the iterations fewer per time step, it's again going to be a quicker simulation. Point triple zero two. Yeah, yeah. So calculate. So now you'll see that there are two windows, console and the graphics window. So this is the console where the residuals are going to show up their values. But if you go to graphics, visually it is easier for me at least to keep track of what is going on. So this is going to evolve, and there would be fluctuations, of course, but after a certain period of time, the fluctuations would be within a certain range, and that implies that it is going closer to stabilization. But still, as a good practice for our published works, we always maintain that high number of time steps before we use the simulation. So this is anyways going to stop after 50. So it's already at 23.
Sir,
Yes.
since total time for the air flowing, like breathing inlet breathing time, that is 3.
No, the time that I'm imposing over here is the time it's needed for the flow to be stable in the airway. Now the breathing time interval is different. We are not tracking that aspect of the process. We are looking at a snapshot in time how the flow field has developed once it is well developed. But if you are trying to think about that time varying effect, no, we are not capturing that. And that is going to be on the order of, so the total breathing in, breathing out is around 5 seconds. And that I'm not discounting your question, in the sense that that is something that could be studied as well. Like what happens if we run the simulation such that we cover 5 seconds? That would take long. That can take on the order of, with the computing powers that I have, if 0.35 seconds take a day, Think about how long 5 seconds would take. We can do that. But the thing is, once the inhalation phase is done, uh, the way the particle is coupled with the flow, we are trying to get the drag force, right? So the flow goes up and goes down. We cannot use the field when it goes down. We have to use the field in the mean region. So that's why we are taking this value once the flow is well developed. But you are trying to simulate the whole inspiratory phase. That has its importance, maybe for heat transfer, but not for particle transport. But on the other hand, if you develop a two-phase simulation where you are where the particle impact can impact the flow field, then you should probably think of it as a 5 second flow or a 2.5 second flow for the inspiratory cycle and see where the particles go with that. Because now it's a two-phase system, right? Does it make sense? But then again, the computing demand would be much higher. So something to think about in future. Yeah. So this is going on. I think. Where are we?
Where are those periodic spikes happening?
The periodic spikes. I don't know numerical artifact. You know way better than me.
Rahul, do you have any idea? Why do these periodic spikes?
Steady you see a smooth curve overall. And these spikes stay, they run in but eventually it fluctuates within a certain range. Okay, so we are done with 12% of the simulation, which is so what it is going to do is 50 times 20. So it is going to go till 1000 over here. So we are till 124. So it's going to go till 1000. So it's going to take half an hour or so. Let's not go till that. But the thing is, you now have a good sense of how the simulation has to be started, right? And you can follow the protocol to do that. So you get the mesh file imported into Fluent and start the simulation. And you can then, once the simulation is done, this is important for especially folks who have not used ANSYS Fluent before. Go to File and then save case and data files. Case file is the one that includes the mesh information and the numerical setup that we have built up. The data file is the data that is going to be generated. Okay, so you have to save both case and data files, and that is available from this file menu. So file, save case and data. I'm going to close this simulation now. How long do we have in this session? Till when?
When it started, 11:15. Half an hour, like 20 minutes.
Okay. So let me do show you something else from the simulated file now. Okay, let me just close it. I should not take up this computing time on my machine there. So I'm closing the simulation, but I will open the one that I had saved on your cloud folder. Okay, so now to open a saved simulation, which you can do because I have already saved the simulations, go to File, then read case and data. Before, when we were just including the mesh file, right? Importing just the mesh file. But here, since you have the data simulated already, so case and data, and go to the, let me go to the Gyan simulation files. So, and the folders on your cloud folder, they have the same names. So go to Fluent for Sims, and this is the flow, the just the flow field. So don't go into the subfolders, just pick this one, this last one, and okay. So although in that pop-up launch window, just the case file shows up, but since you already chose case and data from Fluent, it would also pick up the data file as it brings the information in. Funny thing, Devranjanda is my PhD roommate now works for ANSYS.
Okay.
So he's in sort of like maintenance, those kinds of things. So
Does
he
he like look into the algorithms also?
I think
Like,
so. I don't know the details of what he does now,
okay.
but he worked with an out and out computing guy at Virginia Tech.
So all the things which we dismiss as artifacts, we may have little more to of our server.
Yeah, let me see if I imported the correct simulation. So to get the output data, so there's some simple things that you can directly get out of this window. If you go to reports over here, so go to flux and then the mass flow rate. So the left airway, sorry, not the left airway, the inlets and the outlets are left nostril, right nostril, and the outlet. So compute, close. So what do we see on this window? I hope you can read them. So basically, this is the air flux going into the left nostril, point 0.000329. This is the air flux, point 0.000268, going into the right nostril. What does that tell us to begin with? The flow is asymmetric. To generate a 30 liters per minute flux through the tracheal outlet, through the nasopharyngeal outlet, the two noses, they contribute differently. So sometimes based on the study that you are trying to pursue, that itself is a very important information, how asymmetric the two sides of the nose could be. Now this net is not important. It is just they are trying to sum it up. The other important factor is the outlet, and the negative sign is important because there the flow is escaping the numerical domain, so hence the negative sign. But you see the value that we have achieved, 0.00059. What was the targeted value? 0.0006. So the simulation has worked. Now sometimes it might not work. Sometimes you might end up getting a value which is more than what the error could be more than what you probably can sort of accept. So let's assume that you got a value which is 0.22054. That would be hard to publish on, right? Like you cannot really validly claim that 0.22054 is 0.206. So then you might have to redo the simulation, make sure that the pressure values get changed a little bit, and you can also do a convergence, an interpolation study, as in you can run two simulations, figure out which particular pressure values led to what kind of flow rate, and then you can interpolate those pressure values to figure out at what rough value of the pressure drop we would get a 30 liters per minute flow. But we got lucky here, and many times we do get lucky, and we got a outlet flux that is 30 liters per minute. So you should save this particular window every time you do this kind of work. And from here, the other thing that I would like to show is this is the flux. Let's look at the pressure drop. So for that, go to the surface integrals, and there the report type would be area weighted average, and again pick the left nostril, outlet, and the right nostril, and then compute. So now these are the pressure drops. Again, there is asymmetry between the left and right sides, and then the outlet is something negative 27. Because we used targeting in our scheme, it did change from negative 50 pascals to something else. Now, we also have to report the delta P. To report the delta P, what I do is I take this absolute pressure of the outlet and figure out the mean of these other two, and then subtract that from here. So let me go to your printed pages, and there is an example of this, but it's a different simulation, the one that I have included in the printed pages. But can anyone show me the page if you can find it? Not this one. So basically, it's this one. Yes. So you do understand how we get the delta P, right? But let me just show you over here. Okay. So the numbers are different to what we found in the simulation, because when I was preparing this lecture note, I was using another different simulation with a slightly different kind of a mesh. But the concept is still same. So this, just for the sake of record keeping, let me show the conversion. So this is in kg per second. So this is 0.00059836736, and I'm converting it back to liters per minute. So this should be multiplied by 60 times 10 to the power of 3 divided by 1.204. Can you give me this number? Huh? 29.81. So 29.81 liters per minute. So very close to 30 liters per minute, which is what we wanted to achieve. Now over here, so that is the flow rate, which we typically report as the first thing, and then from here we are getting the pressure drop. So we have the outlet pressure. So this would be delta P, which is minus 27.52 minus half of the two other pressures. So 19.31 plus 2.19. Actually, this would be plus, right? Because you are going to get the delta P. So what would be this number?
minus 38.27.
No, it cannot be
There's the plus sign.
there's a plus sign. Yeah, minus 16.78. Now, once you run the simulations yourself, I would like to you guys to update these numbers because the numbers would be different because this simulation had an error which I later on found out just before traveling. But the generic way, the way we do the calculation and report the data is like this. Now, these are some streamlines from the same simulation, from not from the wrong simulation, but from this simulation that you have saved. So, the things to note could be connected back to what we had studied for the first few days. So look at what the velocity magnitudes are. The range is 0 to 5 meters per second. It starts out with something which is very close to 0. So on the order of 1 meters per second, let's assume. And the maximum it gets is 5 meters per second. Now, if you remember one of the problems, I had assumed the flow to be 5 meters per second. Here is the justification for this, but also with 1 meters per second, as we found, even if the flow is slower, the problem that we were trying to solve was how long does it take for a 100 micron particle to deposit, and we saw that the time interval is so short that it is going to deposit in the anterior parts of the nose. Okay, so you can generate this kind of visuals as well based on what kind of post processor that you might be using. I am not going to go into post processing in this course. uh, Different groups have different favorite processes. What we do is use field view, in case if you want to know the name, but you can use other processes as well. By the way, what post processor did you use? Tekla. Okay. Okay, so this is the flow simulation. Now, if I go again back to the simulation here. mm, so this is so do run the calculation with these numbers later on. So the flow simulation is saved. Now we are going to use this to do the particle tracking. Let's stop here, right? It should be close at 12:15, right? 12:15 is the closing time. Yeah. So in the next session, we are going to first show how to figure out the location of the nozzle if you have a nasal spray, and for that we have to go back to ICEM for a brief while, and after that we are going to come back to the fluent world and set up the particle tracking, run some quick particle tracking simulations, get the data, and for that you guys have to do some calculations as well on some of the printed sheets, and then we are going to compare that with some published paper. I think we can get it done in 1.5 hours, but maybe comparing with the published paper could happen in the last session. And then, based on your availability, you can head over to the CAD lab and test out the files. Okay, so does that sound like a plan? Okay, so let's wait for now. Thank you.
So meet at 2 again here. Fuller